Design IRCTC. The user should be able to query trains between two stations. The query should be based on date, quota, source from, to, destination. The user should be able to see the availability in the train list retrieved from the above query. So it shows the list and shows the availability next to each train. The user should be able to book tickets for the available seats. So it's this IRCTC, it's like a train booking, public transportation booking service or application. The constraint: there will be a huge number of people requesting the service. Because it's a public transportation, the demand will be high, lots of people will be requesting it at the same time. Let us suppose 0.01% of the population use the service daily once. Geo redundancy should be provided. So it's based on geographic, and redundancy should be provided. More read query request than write request, of course, just like any public service. Design. The basic architecture from the scalability theory topic can be used here too. So the basic architecture, where it shows the users and the load balancers and web servers and database servers, can be used here too. On the CDN, there should be a huge number of services which are serving the user, or which are serving users. There should be a huge number of servers, because it should be responsive and the demand will be high. There should be multiple servers at multiple geolocations to provide geo redundancy. To have distributed design architecture and to avoid disconnection and to have redundancy, geo redundancy, we are supposed to spread servers geographically. The database should be replicated at these geolocations, and the database should be synced between them. There may be multiple servers in one particular zone too. There is a huge number of read query. The user generally does a large number of query to find the seat he wants to book, he or she, right? The user. There will be more reads than writes. So master slave, than, not then, right? THAN. And number 5, queries can be cached. Little all data is okay, because the schedule for the train does not change frequently. So there should be a time to live, TTL. 6, all the search will be served by slave servers. When we book a ticket, then the transaction goes directly to the master slave. Locks on train number can be taken to prevent race conditions. Locks on train number can be taken to prevent race conditions. Once a lock is required, that's a nice thing to prevent racism. All right. Once a lock is acquired, then only you can book a ticket. Some counts can be used to avoid unnecessary locking, and some counter can be used for this. That's nice. So number 7 is pretty interesting. Number 8, each station has a quota. So we are still designing. We are adding the functions, right? Each station has a quota and train, and seats are allocated for that quota. So it has a limited. Number 9, each physical train will have two train IDs. One when trains go from source to destination, and one when it comes when trains, not trans, they're missing I, right? Once when, and like another idea, when the train comes back. So in the system, there will be two train IDs for each trip. The fourth, the back and forth, the going will have an ID and the returning will have another ID. Keeping these two separate IDs will make the query easier to implement. For technical reasons, to make the query easier, we do this. And number 10, when final charting is done, then each seat is swapped for the empty slots, and we try to find the request from the source station whose destination is also in that slot. The first fit is allotted that seat. Number 11, a load balancer is used to distribute traffic. And number 12, in the design, there may be multiple booking servers which ask for booking token to the master server. Master servers allocate a token for the server and reserve it for some time. When all the user information is filled and payment is done, then only it allocates real seat depending upon user preference. And the final point in the design, slave server will handle user request till the end. Final booking request with the user payment and his complete information will go to the master server, and the corresponding ticket will be booked. And that's all for the system. Another example, another possible question might be asked during the interview. How would you design an alarm clock? Just alarm clock. How do you design it? The use case. Alarm clock should have all the functions of clock. Should be able to show time. The user can set the alarm time, can reset it, and can set alarm. So can set the time, reset the time, and set alarm. Constraints, the granularity, the precision of alarm can be 15 minutes. So that's a constraint. Set the alarm at some time, for example 6 a.m. and set it. The alarm should work at 6 a.m. Stop the alarm, then alarm should stop ringing. This is how to test it. And the design for the system, there can be a clock class. We create a clock class which manages time and show. This is not shoe. Shoe is something to wear in the foot. This is show, W instead of E. And so manages time and show time to the screen or at the screen. It has functions. The method in this class is get time, set time, right? Alarm clock, extend clock. So we have a basic class that's called a clock class. And alarm clock, extend that, so it's an extension to that, and have some functions like set alarm and stop alarm and set alarm time and ring. So we have this clock class, get time, set time methods, and alarm clock, which is a child class of the main one of the clock class, and it has these methods: set alarm, stop, set alarm time, and ring. And the implementation, a timer entry will run for regularity of 15 minutes or 1 minute, depends on customer's requirement, right? Or 1 minute. It will check if current time, alarm time is true, then ring. If the alarm is on, if start alarm is called, it will set alarm on. If stop alarm called, it will set the alarm off. So it will turn the alarm on and off depending on calling the method. And that was the second question, possible question during the interview. And the third one, it could be design for elevator of a building. Design a lift, an elevator. that we use to go up and down in buildings. Scenario: a typical lift has buttons, elevator buttons inside the cabinet, unlike the user who got the lift to select her desired floor. Similarly, each floor has buttons: floor button to call the lift to go to floors above and floor below, respectively. Buttons illuminate, indicating the request is accepted. In addition, the button stops illuminating when the lift reaches the requested floor. So it turns on once we press it. Once it reaches the destination, it turns off. Right? Use cases: presses the floor button to call the lift, presses the elevator button to move to the desired floor. Floor button and elevator button illuminates when pressed by user, places an elevator request when pressed, and the elevator moves up and down as per instructions, closes the door. The design: each button press results in an elevator request which has to be served. Each of these requests is tracked at centralized place. Elevator request: the class stores elevator request can use different algorithms to schedule the elevator request. The elevator is managed by a controller class, which we call elevator controller. Elevator controller class provides instructions to the elevator. Elevator controller reads the next elevator request to be processed and served. And here's the design. Elevator class, elevator door is a child of it, elevator controller is a child of it, floor door, button, they are all children of the elevator controller. And scheduling algorithm: first in, first out, shortcut first, and elevator button and floor button with their IDs and all that stuff. The button is an abstract class defining common behavior like illuminate, do not illuminate. Floor button, elevator button extends button type and define place request method, which is invoked when a button is pressed. Here is the design for the classes. What classes to be created, how to do the object-oriented thing. We are doing this here. When a floor button or elevator button is pressed, a request is added to a common queue. Elevator controller reads the next request and instruct next action to the elevator. How can we extend this to multiple elevators? In a single elevator scenario, there is a single elevator and an elevator controller and common server where the floor request and the elevator button request are stored, which are processed as per the scheduling algorithm. To extend this to multiple elevator scenarios, there will be still a single elevator controller. Floor-based request can be served by any elevator, whereas elevator button request will be served only by the elevator to whom the button belongs. Floor buttons place request, this is the method, adds a request to the common queue, which is accessed by the elevator controller, thereby assigning the request to one of the elevators. Elevator buttons place request adds a request to the elevator directly as it's supposed to serve it. Elevator controller will be running various algorithms like short test, seek, etc. to decide which lift is supposed to handle which request. In the next video, we'll be talking about another interesting possible interview question, which is design a valet parking system. See you later.